Grounding and bonding for network-powered communication systems, specifically Power over Ethernet-type radios, are crucial for safety and code compliance, particularly under NEC 830. We'll explore the correct methods for grounding and bonding these systems in various applications. Firstly, let's consider the application involving a wood pole. The antenna is mounted at the top of a 60-foot wood pole, with rigid conduit running from a building 100 feet away. This conduit extends up the pole to a junction box, followed by metallic cell tied to the radio. In this scenario, the rigid conduit from the junction box to the antenna can serve as the grounding conductor. A separate ground wire from the antenna to the top of the pole is not explicitly required by NEC 830. For the pole itself, the rigid conduit running from the building to the junction box provides the grounding path. A ground rod is required at the base of the pole and must be bonded to the conduit. At the building, a grounding electrode system, abbreviated GES, must be installed. The rigid conduit entering the building must be bonded to the GES. Secondly, we address the scenario of mounting the radio on a steel water tower. Similar to the wood pole application, the rigid conduit from the junction box to the antenna can serve as the grounding conductor. A separate ground wire from the antenna to the top of the water tower is not required under NEC 830. The steel water tower itself serves as the grounding electrode. Therefore, no additional grounding is specifically required at the water tower. However, at the building, a grounding electrode system, abbreviated GES, must still be installed. The rigid conduit entering the building must be bonded to this GES. Thirdly, let's consider the application where the radio is mounted on a rooftop next to a video camera. Both the radio and the video camera are powered by 120 volts low voltage transformers. In this case, a common grounding electrode must be connected to the grounding conductor of the power supply for the transformers. The common grounding electrode can be the metal conduit or cable raceway feeding the transformers. A separate ground wire from the transformers to the building structure is not mandated by NEC 830. At the building, a grounding electrode system, abbreviated GES, must be installed. The grounding conductor from the transformers must be bonded to the GES. Now, regarding lightning surge protection, while surge protection is not explicitly required by NEC 830, it is highly recommended to protect electronic equipment, including network-powered communication systems, from lightning surges. Surge protection devices can be installed either at the building entrance or at the equipment location. This protection becomes especially vital when the radios are fed using either a Cat5-type cable or a coax-type cable, as these can be susceptible to surges. Here are some additional considerations. The number 6-stranded copper wire is not specifically referenced in NEC. It's a common and practical choice for grounding purposes. The antenna, mounting hardware, and conduit should be bonded together at each connection point to ensure a continuous grounding path. Grounding conductors must be protected from physical damage and corrosion, ensuring their long-term effectiveness. Finally, all grounding connections should be tight and free of rust or paint to maintain a reliable electrical connection. These measures help ensure compliance with NEC 830 and promote a safe and reliable network-powered communication system. The grounding electrode system, abbreviated GES, is a critical component. It's the means by which the electrical system is connected to the earth, providing a low impedance path for fault current. Common grounding electrodes include metal underground water pipes, metal frames of buildings, and ground rods. The specific requirements for the GES are detailed in NEC Article 250. It's essential that the GES is properly installed and maintained to ensure effective grounding. Bonding is another crucial aspect of grounding and bonding. Bonding involves connecting all metal parts of the electrical system together to create a low impedance path for fault current. This includes bonding the metal conduit, equipment enclosures, and other metal parts of the system. Bonding helps to equalize the voltage potential between different parts of the system, reducing the risk of electric shock. The NEC provides specific requirements for bonding in Article 250. In addition to the specific requirements outlined in NEC 830, it's important to consider general grounding and bonding principles. These principles are based on the understanding of how electricity flows and how to minimize the risk of electrical hazards. A well-designed and installed grounding and bonding system is essential for the safe and reliable operation of any electrical system. The NEC provides a comprehensive set of rules and guidelines for grounding and bonding, and it's important to follow these rules to ensure compliance and safety. Remember to always consult with a qualified electrician or electrical engineer when designing or installing a grounding and bonding system. They can help you to ensure that the system meets all applicable codes and standards and that it provides adequate protection against electrical hazards. Grounding is not about providing a path for electricity to flow under normal conditions. It's about providing a low impedance path for fault current to flow in the event of a fault. This allows the overcurrent protective device, such as a circuit breaker or fuse, to quickly trip and to energize the circuit, preventing electrical shock and fire. The impedance of the grounding path is critical. A high impedance grounding path can limit the flow of fault current, which can prevent the overcurrent protective device from tripping. This can result in a dangerous situation where the metal parts of the electrical system are energized at a high voltage. The NEC specifies the maximum impedance of the grounding path in Article 250. It's important to use the correct size grounding conductors to ensure that the impedance is low enough. The size of the grounding conductors is determined by the size of the overcurrent protective device. The NEC provides tables that specify the minimum size of grounding conductors for different size overcurrent protective devices. In addition to the size of the grounding conductors, the quality of the grounding connections is also critical. Loose or corroded grounding connections can increase the impedance of the grounding path. All grounding connections should be tight and free of rust or paint. It's also important to protect grounding conductors from physical damage and corrosion. Grounding conductors should be installed in conduit or other protective enclosures where they are exposed to physical damage. Corrosion can be prevented by using corrosion-resistant materials or by applying a protective coating to the grounding conductors. Regular inspection and maintenance of the grounding system is essential to ensure that it remains effective. Grounding connections should be inspected periodically for tightness and corrosion. Grounding conductors should be inspected for physical damage. Any problems with the grounding system should be corrected immediately. A properly designed, installed, and maintained grounding system is an essential part of any electrical system. It helps to protect people from electrical shock and to prevent electrical fires. The NEC provides a comprehensive set of rules and guidelines for grounding, and it's important to follow these rules to ensure compliance and safety. When working with electrical systems, always remember to follow safe work practices. Wear appropriate personal protective equipment, such as safety glasses and gloves. To energize circuits before working on them. Use lockout-tagout procedures to prevent circuits from being accidentally re-energized. If you're not qualified to work on electrical systems, don't do it. Hire a qualified electrician to do the work. Electricity is dangerous, and it's important to take all necessary precautions to protect yourself from electrical hazards. Remember that grounding and bonding are two distinct but related concepts. Grounding connects the electrical system to the earth, while bonding connects all metal parts of the system together. Both grounding and bonding are necessary to provide a safe and reliable electrical system. The NEC provides specific requirements for both grounding and bonding in Article 250. It's important to understand these requirements and to follow them carefully. There are different types of grounding systems, such as grounded systems and ungrounded systems. In a grounded system, one of the conductors is intentionally connected to the earth. In an ungrounded system, none of the conductors are intentionally connected to the earth. Each type of grounding system has its own advantages and disadvantages. Grounded systems are generally safer than ungrounded systems because they provide a low impedance path for fault current. However, grounded systems are also more susceptible to ground faults. Ungrounded systems are less susceptible to ground faults, but they are also less safe because they don't provide a low impedance path for fault current. The choice of which type of grounding system to use depends on the specific application. The NEC provides guidance on the selection of grounding systems in Article 250. In addition to the requirements of the NEC, there may be other applicable codes and standards that apply to grounding and bonding. For example, the National Fire Protection Association, abbreviated NFPA, publishes a number of standards that address grounding and bonding. It's important to be aware of all applicable codes and standards and to follow them carefully. Grounding and bonding are complex topics, and it's important to have a thorough understanding of the principles involved. If you're not sure how to properly ground and bond an electrical system, consult with a qualified electrician or electrical engineer. They can help you to ensure that the system meets all applicable codes and standards and that it provides adequate protection against electrical hazards.